Okay, in the last video, we got into our data set, kind of saw what we were working with, and we ended on looking at these seasonal plots. Particularly, we were looking for the abnormal data points, the abnormal observations that were sort of these weird spikes showing up in places where they didn't look like they fit with the rest of the data. And so I went through and just cleaned those up. Again, did that manually because to program something like that is pretty difficult. If we were in a world where we had a much larger data set, or this was some sort of production forecasting environment or something like this, then of course it wouldn't be practical to go in and do that manually. But on a relatively small data set of 20 stores, there were only a few dozen data points that needed to be cleaned up. And actually, while I was in there, I found a couple of other just observations that were there but missing a POS value. So I went ahead and did the imputation on those two. Just some general cleaning. Again, it's a small enough data set to handle some of those things manually. And so what you see here is an updated seasonality plot. You'll recall on store 820 we had several odd abnormal observations throughout this, and I'll just scroll through some of these as we did before. You'll see that they look much more standard from year over year. We don't see those sort of odd abnormal spikes. This is an interesting store, 756. It looks like sales have gone down every year, even though the overall shape is the same. The level has gone down every year, so maybe that store is getting ready to close or something. Who knows? But again, you can see that these just look much more smooth overall. The data is relatively well packed together. We don't see any one-off spikes living anywhere that don't look like they fit the data set. So we've cleaned these up considerably, and that really is the goal of any sort of exploratory data analysis. You're just trying to find out where your problems lie and get them cleaned up so that you're ready to do some modeling. And so we're ready. And so I'm going to jump over to another program where we'll do the time series forecasting. And so I'll take you through a few different things here. I'll walk you through first how to just create a time series forecast just for one time series, and then I've written up a process here that'll select the quote best time series forecast. Again, that's going to be determined by a holdout MAPE. So I'll explain how I'm doing that here, and then we'll go ahead and run the forecast for all the stores, and then find the average MAPE for this value. One advantage of MAPE is that it really is unitless. So RMSE is really dependent on the scale of your data. So if you use RMSE as a fit statistic, you could get a value of 100,000 and it wouldn't, if you're talking sales in the millions, then 100,000 is pretty good. If you're talking about human body weight, then 100,000 is a pretty bad value. But RMSE, the point there is that RMSE is dependent on the scale of your data. MAPE, on the other hand, is a percentage error. So it's not really. 5% error is 5% error no matter what the scale of your data. And so that's another advantage of using MAPE. So the level of sales in all these stores are different, but when we capture MAPE, a 5% error in one store is the same as 5% error in another store. We know obviously in units that would be different, but it puts the error measure in the same scale for all of the stores. So we'll go ahead and capture the average MAPE just to get a sense for overall for our time series method, how does it perform? And so we'll capture that. So first, let's just look at how to create a time series forecast. I need a function to calculate MAPE, first of all, and so there isn't really a good one in R. You can select it as an option in certain forecasting functions, but to calculate directly, there isn't really a good one that I'm aware of. So I'll just create one, and so it's relatively simple. You take the absolute difference, you divide it by the predicted value, and you multiply by 100 to get the percent. You want the mean of that, and that's what MAPE is: mean absolute percent error. And so it's just a simple calculation there. We also need to define our forecast dates. which again will be the month of October for 2012. And so we have October 5th, 12th, 19th, and 26th. So we'll just create that date vector. It'll help just kind of keep all of our data together when we're mapping these different week values together. And now I've written a loop here that'll run the forecasting code for each store. Remember, we're going to break apart and take one store at a time, turn it into a time series object, and then forecast it, and then we'll store all of those together. And so that's what this big loop does. It's pretty dense code. I understand that. We won't take the time to go through every piece of it, but I'll give you the highlights. So we'll break this up and run this. This is our forecasting algorithm where we'll extract one store and create a time series. We'll create an ARIMA forecast. We'll create an ESM forecast, and then we'll select the better of the two and then put them all together. I see these say RMSE. I must have had RMSE on the mind for some reason. These are going to be MAPE values, of course. And so what we'll do here, let me first show you just how we would create a forecast for one store. So this is going to be, this loop is indexed on the value I. So let me just initialize I to be 1, and then I'll capture whatever stores I is. Remember, stores is our list of store numbers, and so the first one in the list is store 1061. So we're going to extract the data for that store, create a time series object out of it. So this is just extracting, store number equal to 1061. So we'll get the store. The NA trim time series is going to delete all of those leading NAs from different cases. Could not find function NA trim TS. Okay, NA trim.ts actually comes from a different package that we forgot to load earlier. So we need the zoo package. Great. Okay, the zoo package uses this NA trim, and so again, what it'll do is it'll take all of those leading NA observations and just delete those. And so we have now, if we look at TS, let's go ahead and view what TS looks like. It's just our total POS values, and so that's for one of the stores. And so we have 139 observations. This is for store 1061. And so we're good there, but it's just a column vector with the total POS values. So what we need to do is turn those into a time series. Now, I'm going to use here a 4-week holdout sample. And so recall that our validation technique on a time series is going to be the holdout MAPE. So our time series has 139 observations. What I'm going to do is create 2 time series, a short and a long. So the TS short, time series short, is going to peel off the last 4 observations. And so that's what this does here. I want the TS object that we just created, but I only want observations 1 through not the last 4. So take the length and subtract 4. And so that'll give me 135 observations. We'll use those 135 observations to build our model, use that model to forecast the next 4 weeks, and then we'll have 4 weeks of actuals that we can use then as a test set to see what the MAPE is over that test set. So TS short will be have the most recent 4 weeks held back. TS long will be the entire 4 weeks. And so what we'll do is, again, build the model on TS short, use that to forecast the last 4 weeks and collect the MAPE. We'll do that for the ARIMA and for the ESM. And then we'll get whichever model is better, the ARIMA or the ESM, we'll use that to go ahead and forecast on TS long to create the forecast for the entire time series. So we'll use TS short again as kind of a validation set, and then once we know which one is better, we'll take the forecast for the whole thing using that model. So for 1061, TS short, you'll see here it's only 135 observations. The other thing you'll notice is different is that we're setting the frequency to 1 here. instead of 52 that we did in the previous video. And the reason is that when it comes to time series modeling, a seasonality of 52 units when you're actually building the model is pretty troublesome because not every year has 52 weeks. In fact, some years have 53 weeks, just kind of depending on how the calendar is built. And so having a frequency of 52 is not exactly correct. The technical week number frequency is 365 and a quarter divided by 7, because you have, there's 365 days in a year, or 365 and a quarter days in a year, technically divided by 7 days in a week. And so you get sort of a decimal frequency, and so it's really tricky. The nice thing is that in R, this TS function that'll create a time series object is basically dumb. It doesn't know a week from a day, from a year, from a minute. And so by setting frequency equal to 1, we're basically pretending that every observation is a year, but in R it doesn't matter. All R knows is that every observation is the same distance apart from the ones next to it. So whether that's a year or a week or a month or a day, again, just doesn't matter. So we'll just set a frequency of 1. To get around that. In fact, if you set a frequency of 52 here and try to model against that, you'll get an error. R really doesn't like a frequency of 52 or a frequency of the decimal approximation either. So TS short is 135 units, and then TS long, we'll see it over here, is 139. Okay, so again, the TS short has the 4 weeks held back. Now, what we'll do then, and we'll just look at this ARIMA chunk here. ARIMA short is going to create a forecast on TS short, so only on the 134 weeks. These other two things are parameters that help select the best model. So inside an ARIMA model, you can have a lot of different components in an ARIMA model and a lot of different orders. And so the auto ARIMA function will test all of that and pick the best one, even in the ARIMA family. And so we're passing just some criteria here. We're telling it what statistical test to use. This is the augmented Dickey-Fuller, is what ADF stands for, and that's going to be the standard. And then the information criteria is AIC. So you can use AIC as BIC or the Schwartz. And so I'll just use AIC because that's the one that most of you will at least have been exposed to. So this will create a model on the short time series. And then the ARIMA holdout MAPE is going to be the MAPE function applied to the actual time series, but our 4-week holdout sample, and then our forecast on ARIMA short. And so the way time series forecasting works in R is that you're going to use a modeling function. So in this case, either we'll use auto ARIMA, and then the one we'll use for exponential smoothing will be ETS down here. That actually creates a model. So it creates the terms in your model and all the parameter estimates. And then you use the forecast function to take that model and actually create forecasted values. And so we pass it the ARIMA short model. We tell it we want 4 forecasted observations. This forecast function gives us a lot of output, and so we're going to say that we only want the mean out of that, which would be the point estimate for the forecasts. And so we'll calculate the MAPE on that, and then we'll go ahead here and calculate the ARIMA forecast, which again is going to be the forecast function, but now on the entire time series. So on the TS long object, which is the full 139 observations. Again, the model here is the ARIMA short. And then we want to forecast 4 weeks out in advance, and that's the 4 weeks in October of 2012. And you can see we have the exact same structure here for the ESM forecast. We'll use the ETS function to create the forecast on TS short. And then we'll calculate the MAPE of the holdout forecast, and then we'll calculate on the forecast for long. And so we can go ahead and run this. And so that creates, it's just that quick, creates a forecast object. We can create the ARIMA holdout MAPE. And so we see here ARIMA holdout MAPE is about 2.15. Right, so that's a pretty good fit, 2.15% error across the 4 observations. And then we'll go ahead and create the ARIMA forecast, which is going to use the ARIMA short model, but on the entire long time series. Okay, and then we could do the same thing for ESM short. We can calculate the ESM holdout MAPE. Here we see the ESM holdout MAPE is actually smaller. It's 1.38, and so in this case, the ESM would be the champion. And then we can create the ESM forecast as well on the entire time series. And then this other code here is just compiling the results. So, if the ARIMA holdout MAPE is less than the ESM MAPE, then we're going to capture the ARIMA forecast. And if it's not, then we're going to capture the ESM forecast because that one's better. And then here is just kind of collecting everything in this data set called TS Thickest. And so this is just about compiling the data. So again, this is really how you create a forecast for one time series forecast and then select the quote unquote best time series forecast, right? And so we'll go ahead and run this whole loop, and it'll go through and take just a second to run here, and this will actually run through and run that same process for each of the stores in our data set. And you can see that it's done already, so it's a fairly quick process. 20 stores, we have 20 forecast values. And so what we'll do here is just clean up in this TS Thickest. We need to clean up some of those values. And let's go ahead and take a look at this TS Thickest data set. So what we've captured here then is, we have our date keys. So it's October 5th, 12th, 19th, and 26th. We have the store number. We have the champion model type, the predicted values, and then what the holdout MAPE was for those for that particular model. And so you can see, if we look at model, we can see that ESMs and ARIMAs appear about the same amount of frequency. So it's about half and half. A couple other things to note. The ESM model, you'll see on this one, this ESM, actually the first two ESMs give us a flat forecast. So the time series prediction is the same value for all 4 weeks. Compare that to like this ARIMA model gives us a different forecasted value. And that's pretty common output. Again, ESM here is the same. That's pretty common. In ESM, it's very common to get just a flat forecasted value. So there's nothing abnormal going on here. And it's common with ARIMA to not get to get a flat forecasted value. So these look like pretty standard outputs. Here's an ESM where we do get different values for the 4 weeks. And so we're just collecting the results here again so that we have that. A couple other things we want to do. We want to capture the average MAPE for the time series. And so this is the average holdout MAPE, of course. So the TS average MAPE was about 5.95, so just under 6%, just under 6%. And if we look at that, we're just averaging this holdout MAPE column. So you can see, here we had below 2. This case was 5.5. This was up above 10, up above 11. We have some that are around 6, 7, a couple others that are around 2. And so if we take the average of all these values, the average MAPE, here's one that was 18. That's really a poor fit. But I guess it was better than the ARIMA. But the average across all those cases is just under 6%. So that's pretty good. That's a pretty good MAPE value, especially forecasting across multiple stores like that. 6% is very good. Now, if we want, we can just take the last ARIMA short value that we have, and I'll show you what it looks like to kind of plot these. There's your actuals, and then here is your forecasted value in the blue line. And so this is, you can play around with this on your own, but the red line would be the actual values, and then the blue line would be the modeled values out of our model. And I don't know, this looks like it's probably an ARIMA model. ESMs tend to be a little bit more smooth, which is why we get, flatter forecasts. You can also forecast just the 4 periods ahead using just the plot function. So it tells you kind of what the model was. This is an ARIMA 100. We won't get into a lot of the details about what that means. But you can see that, again, here's our actuals, and then here's where our point estimates end up being. So you can tell it picks up that this thing's coming up. And then the shaded regions here are your confidence and your prediction intervals if you're interested in that sort of thing. And all of that is included in the model output if you wanted to access those. We won't use them here, so we won't get into how to get to those, but it's pretty standard R syntax if you want to access the model output there. And then you can play around with capturing those. Let's go ahead and look at the ESM forecast here. Oh, well, it's going to make a liar out of me. In fact, the ESM forecast was actually had more spikes in it than the ARIMA forecast. I'm surprised. This is fairly uncommon. Typically, your ESM forecast, like I said, is going to be quite a bit flatter. So you can see here that the ESM, even at the end, really takes a dip down on the training period, and then we do get a flat forecast here again on the actual forecast window. And that's pretty common stuff. So those are just a couple of ways that you can plot your actuals and your forecasted values so that you can see what you're looking at. Again, we won't take the time to go through all of those, but or talk about all the syntax of everything that we've done here. But you can kind of look through that. We've hit the main forecasting functions that you need. And the main takeaway is that now we've got our four forecasted values using the best time series model for each individual store. And so that's going to do it for this video. In the next video, we'll get into the gradient boosting modeling and look at how we need to interact with the data a little bit differently in that scenario and how we'll build that model as well.